Good morning, everyone, or good afternoon, depending on when you're watching this video. In today's lecture video, we are going to pick back up talking about the FFT method to solve problems in spherical coordinates. And in today's example, we are going to be solving a problem in spherical coordinates that involves both r and eta. So what you see on the screen is the governing equation for a spherical problem that involves r and eta, where again, we do not have any type of volumetric generation term, whether that be some type of reaction or whether that be a heat source in our system. For these particular problems, for us to have one linear independent solution, these problems have eigenvalues that take the form of the following. And then in terms of our basis functions for these problems, so what you'll find in Dean, let me go ahead and clear this up. Oh, this is not the right one. Nope. Here we are. Okay, in Dean, table 5.6 gives us the first four basis functions for these particular problems. Again, we're talking about problems that involve r and eta. And what you see in the leftmost column is the collection of Legendre polynomials. We're just going to call those LG polynomials. And what you see is, again, the first four LG polynomials going from n equals 0 to n equals 1. And those basis functions are generated from those LG polynomials. We can calculate an infinite number of those polynomials based on the following formula that I pulled from Dean in Appendix B. And then how do we calculate those basis functions? Well, we calculate those basis functions using the following equation. Here you'll see that our basis function is in terms of our variable eta. Therefore, our transformed variable is going to be in terms of r. Okay, so let's solve an example problem for this particular scenario of a spherical problem that involves r and eta. So the example problem we're going to solve is heat conduction in a suspension of spheres. And if you want to follow along in Dean, this is example problem 5.8-2. Okay, in the example problem, Dean leaves out a good amount of the math needed to get from one step to another. I'm going to spend the time to go through that math so you know where it came from. And so that's why this video might end up being a bit longer than previous videos. So in this particular scenario, we're going to imagine we have a dilute suspension of spheres, and we're going to subject that suspension of spheres to a temperature gradient. If we have a dilute enough suspension, it's sufficient for us to write our boundaries or concentrate our control volume on a single sphere. Right? We're going to call that sphere material B, and that sphere is going to be surrounded by a second phase that is infinitely large, and we're going to call that material A. So I already spent a bit of time putting a drawing together. Let me bring that back into frame. So here's our scenario. Again, we have a single sphere of material B. It is surrounded by an infinitely large sink of material A. The goal of our problem is to derive the temperature profile both inside material B as well as in the surrounding material A. For that, we've defined the temperature variable inside our sphere as lambda, and the temperature variable in material A surrounding our sphere as psi. Okay, so there is a steady heat flux that results in a uniform temperature gradient G that operates in the Z direction far away from the sphere. And so what we'll see when we get to fluid flow is that this is traditionally referred to as a far field condition because it gives me information far away from my particular control volume, in this case, the sphere. What am I saying mathematically? I am saying that the sphere is subjected to some temperature gradient, and that temperature gradient is equal to G, and it operates in the Z direction. For this particular problem, I am solving in terms of R and eta. So I need to convert that temperature gradient that I'm given into the coordinate that I care about. Eta, the variable eta, is taken care of with the basis function. And so what I'm really looking for here is some measure of how the temperature changes with R. To make this transform, what I need to do is I need to go in the back of my book. I need to go to Appendix A. And that is on page 632, where I'm going to pull this identity. And so on page 632, I can find the following identity. And this is for spherical coordinates. That unit vector in the Z direction in terms of spherical coordinates is equal to the cosine of theta, unit vector in the R direction minus sine of theta, unit vector in the theta direction. So I can plug in or substitute that identity that I pulled from the back of the textbook into my unit vector in the Z direction. Therefore, if I take the partial of temperature with respect to the R direction, I end up with G times cosine of theta. If we remember, this variable change that we made was eta is equal to cosine of theta. Therefore, our temperature gradient is G times eta. Okay. So first thing we can do is write the governing equations for both material A and material B. So let's start with material A. All I'm going to do is come back up here to my governing equation, my general governing equation, and substitute in size where I see thetas. And I end up with the following governing equation. So that becomes my governing equation for material A. I'm going to go ahead and define one of the boundary conditions for material A. That boundary condition I can take from my far field condition, because again, that far field condition is giving me information about what's going on in material A far away from the surface of that sphere. I am told that the temperature gradient, so in terms of my variable for temperature for material A, that's d psi dr. This is at r equals infinity, so infinitely far away from the surface of my sphere. Is equal to g eta. Well, this is a two-dimensional equation, so far away from my sphere and for all etas, g eta. Right, for now, I'm just going to write that one boundary condition. I'm going to move on, write my governing equation for material B. It should look exactly the same as the equation I just wrote for material A, except that I have the variable lambda instead of psi. Much like I did for material A, I'm going to write one of the boundary conditions down for material B. And that boundary condition is going to be that the temperature at the center of the sphere and for all etas is finite. And so this may seem a bit strange for us because typically for cylindrical and spherical problems, and sometimes for rectangular problems, but for rectangular problems, we typically just change our scale. So specifically for cylindrical and spherical problems, at the center of the cylinder and at the center of the sphere, we typically have a symmetric boundary condition that tells us that the flux is equal to 0, i.e. the gradient is equal to 0. Unfortunately, because the temperature varies as both a function of r and eta for us is technically theta, we do not have a spherically symmetric system. Therefore, it is not okay for us to assume that the flux at r equals 0 is 0. So the only thing we can say is that we know that the temperature at the center of the sphere is finite, and that will be enough information to help us solve for one of our constants. Okay, so two differential equations. They're both second order. I've written down two boundary conditions, so I need two more boundary conditions. The two other boundary conditions come from the fact that the temperature and the normal component of the heat flux must be continuous at the interface. So from that, the two boundary conditions I can write. So these are the two additional boundary conditions. The first one tells me that the temperatures are equal. So at the surface of my sphere and for all etas, the temperature should be equal to that at the surface of the sphere and for all etas. The second one tells me that the normal component of my heat flux must be continuous. Therefore, the flux of material A at the surface and for all etas must be equal to the flux in material B at the surface and for all etas. And then I have a term gamma here where gamma is simply equal to the ratio of my thermal conductivities. So KB divided by KA. Now I have four boundary conditions, two second order differential equations. I should be able to solve my problem. Okay, so the first thing I'm going to do, we're using FFT, so I'm going to propose a solution. That solution is going to look exactly the same as it has for all the previous problems that we've solved. So I'll write it, well, I'll write it for both. So for material A, R and eta equal to the summation. In this case, we go from n equals 0 to infinity. I guess we should write that up next to our eigenvalues. Summation from equals to infinity of our transformed variable, which will be a function of r, and our basis function, which is a function of eta. Okay, now the next thing that we typically do is we go back and we transform the various parts of our differential equation. And so I'm going to just pick material A and do the transform on that. There are a couple important things to point out here with the form of our FFT transform. Our transformed variable, we're going to define that as the integral. Here's the first difference. So instead of going from 0 to 1, which we typically do, we are now going to have our integral bound from -1 to 1. That -1 to 1, I might as well write it up here, comes from the fact that our variable change to eta now has a system that goes between -1 and 1. So since our integral is going to be with respect to eta, we are now going to go from -1 to 1 as well. Our temperature variable for material A, we're going to multiply that by the basis function. And then all of that is going to be with respect to d eta. And so that is the second difference between spherical problems involving R and T here, that weighting function that was previously equal to r squared for the spherical problem in our last video is now equal to 1. So the only time we use r squared in our transform is when we are solving problems involving r and t. And we would also need to change the bounds of our integral. They would need to go from 0 to 1. Because we've done this variable transform, we've gone from theta to eta. Our integral is now bounded from -1 to 1, and our weighting fraction, or our weighting function, I should say, is equal to 1. And so we're going to use this form of our FFT transform to go back and transform the individual parts of the differential equation. So we'll start with the first term on the left-hand side of the equation. That left hand, or the farmost left term on the left-hand side of the equation, is not a function of eta at all, so it directly pops out of my integral. I end up being left with that definition of my transformed variable. And so I simply go from a partial derivative to a full derivative, and now I have a transformed variable psi sub n. Let's transform the second term on the left-hand side of the equation. This will look very similar to all the other terms when we've done a transform and had to do integration by parts. Instead of an r squared being out front like it was for our problems involving r and t, we are now going to have a 1 minus eta squared that pops out in the front. Everything inside the bracket looks the same as it has for all other problems. We have the partial of psi with respect to eta multiplied by our basis function minus psi multiplied by the derivative of our basis function. Because our integral was from -1 to 1, we need to evaluate these terms at eta equals -1 and eta equals 1. And then we have the last part, our last term in our equation. That is the eigenvalue squared multiplied by our transformed variable psi sub n. First term goes away. Second term, because we know that the gradient and the temperature are both finite at eta equals -1 and eta equals 1, that second term also goes away. Right? So I guess technically the first term goes away because of the temperature gradient being finite. The second term goes away because the temperature is finite. Finite being an important word here, because technically if I plug in -1 and 1 here for eta, oh, excuse me, I don't want to say that. No, excuse me, I do want to say that. Because if I plug in -1 or 1 for eta, that term out front becomes 0. But if that 0 is for some reason multiplying a non-finite number, then that would be an indeterminate. So just knowing that the temperature gradient is finite at eta equals -1 and 1, and the temperature is finite at eta equals -1 and 1 causes those terms to go away. And I'm simply left with the negative of my eigenvalue squared multiplied by my transformed variable, which I could also write as -n plus 1 multiplied by my transformed variable. I can take those transformed terms, combine them back into a differential equation. And so for material A, I end up with the following equation. Hopefully it's obvious to you that I would go through the exact same procedure to derive the transformed equation for material B. It would look exactly the same, except the fact that we would have a lambda sub n instead of a psi sub n. Okay, so those become our two newly transformed differential equations. These particular equations are known as equidimensional equations, or equidimensional, however you pronounce it. So equidimensional equations, those are discussed in a bit more detail in Appendix D and B, in Appendix B and D, excuse me. Right, the most important thing to know is when we have equations that take this form, that the solutions are of the form r to the p, where p is some unknown exponential. So in the example problem, Dean says, take that trial solution, plug it back into either one of those differential equations, and you will find that the roots are equal to p, the roots are equal to n and -n plus 1. I'm not sure how familiar everyone is with equidimensional equations and coming up with the solution to them. And so it's not clear to me that it's obvious where these roots came from. So I do want to walk you through the math there. So let's just pick one equation because, again, the form of the equations is exactly the same. So the roots that we're going to get, or values for P, are going to be exactly the same for each equation. So let's just start with material A. First, I'm going to expand that nested derivative. Okay, so that is my expanded equation. And then, as Dean said, I'm going to take my trial solution and I'm going to plug it back into that differential equation. So my trial solution is simply that my transformed variable is equal to r to the p power. So I also know that the derivative with respect to r is equal to p r to the p minus 1. And then my second derivative is going to be equal to p times p minus 1 r to the p minus 2. Now I am simply going to take those, plug those back into the above differential equation. When I do that, I should end up with the following equation. Now let me simplify that equation a bit. So all I've done is combine the exponents for my r variable. Those exponents end up canceling out the -2 or the -2 and the -1. I'm simply left with r to the p. I can factor out r to the p. And then I can simplify that down one more time. So I should end up here with this equation. So one way that equation could be equal to 0 is if Rp equals 0. This is what's known as the trivial solution. What we really want to know is when does that term in parentheses equal 0? i.e., what are the roots of that quadratic equation? I can take that equation, I can factor it, And once I factor it, it becomes obvious that the two roots of my equation are p equals n and p equals negative n plus 1, which are the same roots that Dean comes up with in his example problem. Okay, so if that was unfamiliar to you, take a bit of time, rewind the video, go back and see exactly what I did, because these type of equidimensional equations are going to pop back up when we start talking about fluid flow and stream functions. So it's important that you do understand exactly how to solve for the roots of this problem. Okay, now that I have those roots, I can plug that back in to here, my trial solution or proposed solution. When I do that, I end up with the following equation. Same process would occur if I would have plugged that trial solution into the differential equation associated with lambda. So I will end up with the exact same general solution. Okay, so those are my general solutions for the transformed temperature inside and outside of the sphere. And now what I need to do is I need to use those four boundary conditions to help me solve for those four unknown constants. Okay, there's an easy simplification that can be made. That simplification comes from this boundary condition here, which tells me that the temperature in the center of my sphere must be finite. So if I come back down to the general solution for the temperature inside my sphere, I see that as R goes to 0, this term here with the negative exponent blows up, right? Goes to infinity. I end up with some unknown constant over 0. That can't be true because we know we have a finite temperature at the center of the sphere. Therefore, we need that term to go away. And so we can already determine that that constant d sub n must be equal to 0. So we end up with a bit of a simplified equation for the temperature, transformed temperature inside of our sphere. Simply lambda sub n is equal to c sub n times r to the n. Okay, so I know I said that this was going to be a longer video. I'm starting to think that it's probably better if I break this up into 2 parts. This feels like a good place to stop. So I am going to stop here. Put a little line. Part 1. And then we will pick back up at part 2. So where we are currently at is we currently have our 2 solutions for our transformed temperature, both inside and outside the sphere. but we're left with 3 unknown constants. And so we need to use the 3 remaining boundary conditions to help us solve for those constants. And that's where I will pick up in part 2.